All right, guys, section 2.1, problem number 27. They're giving us a word problem here dealing with some type of fungus right here, and our plants are wilting. The field is infected. Okay, gotcha. So a couple of keywords in the directions we have to read right here is that we're dealing with a percentage, f of t here, of infected plants. So this row right here in the table is going to be the value of our function, the percent of our field that's going to be infected. And maybe not surprisingly, it starts at a percentage of 0, and it ends up really, really high, close to 100. And then, let's keep reading here, the time t is measured in days. So this is basically an XY table right here, except we'd probably call it t f of t here, with t being our independent variable on the top for days, and f of t being the dependent variable, y, percent infected, down there on the bottom. So let's take a look at the 4 questions they're asking us here. Part A, what are the units of the rate of change of f of t with respect to t? So what we're kind of coming up with right here, a rate of change function. And if we think about the formula we did for average rate of change, that was always defined as usually delta y over delta x, but I also used this version of it as well, delta f over delta t. And that applies a little bit more to this particular problem, since clearly those are the name of the function, f, and the name of the variable t that we're measuring. So delta f, change in the function right here, is a percent of the field that's infected. So that's going to be a percentage up on top. And down on bottom, the change in time, we're measuring time here in days. So the units right here for a rate of change are going to be percent, and I suppose I should say percent infected per day really would be the rate right here. And that kind of tells you then the answer to that second part. What does the rate measure? It basically tells us how quickly the infection rate is spreading in a certain particular time right there. So the units are going to help you out here. It's percent infected per day. That's the unit right there for part A. Okay, question B, use the graph to rank now from smallest to largest. So here you go. That was part A. We'll pick up part B right here. We're going to rank here from smallest to largest the average infection rates on these intervals here from 0 to 12, 20 to 32, and 40 to 52 days. And since we're talking about average infection rates, these are average rates of change. And remember that when we're talking about average rate of change, graphically, that manifests itself as the slope of a secant line. So I'm going to draw a secant line here that goes from t equals 0, which is at this point right here, to t equals 12. And obviously I'm just guessing where 12 is, but I'm going to say that it's somewhere right around there. And you know what? I'm going to change this to blue, because otherwise that's going to be hard to see on that red graph. And there, oh, that's hard to see too, would be a blue secant line there connecting those 2 points. Now by itself, that doesn't tell me very much. Well, let's go ahead and let's draw the second secant line now. One starting at t equals 20, which is right about here, and then ending at t equals 32, which is right about here. And as we draw that secant line now, the question becomes, how does the slope of this first secant line here compare to the slope of the second secant line? And I'm kind of guessing right here, but it looks like the first secant line, if I were to continue it, would do something like that. It looks like the second secant line, therefore, is a little bit steeper than the first one. Now, the third one they want us to compare, and I think I know what's happening here, begins at t equals 40 and ends now at t equals 52. So here would be the third secant line right there, and that one actually looks the most shallow out of the 3. So I think I know my answer right here, but let's read this again. Use the graph to rank from smallest to largest the average infection rates. So I would say that the smallest, really the lowest infection rate here, would be the least steep out of those. The smallest one would be then the third interval we did from 40 to 52 days. The one in the middle then, the one that's not the most steep, not the least steep, I think that would be the first rate there, number 1, which was measured from 0 days to 12, and then therefore the largest average rate of change, or the steepest secant line, would be the middle one, going from 20 to 32 days. So it's basically a question there, guys, of the steepness of the slopes of those secants. Okay, that takes us through part B. Let's take a look at what they want us doing here in C. Use the following table to compute the average rates of infection over those intervals right there, 3 of them that they gave us. All right, so let's take a look. What am I doing here? So I will label this right here as average rate of change, but the first one being from 30 to 40. Okay, so all of this is coming from the table here, guys. So I'll write this out just one time. What we're really doing here is we're measuring f, the value of the function, percent infected, at 40 days minus f of 30 days, and then on the bottom just the change in t, 40 minus 30. I think I'll go a little quicker through that on the next couple parts of this problem. So here we go, guys. Using the table, f of 40 comes right here. That is going to be a 91 minus f of 30 right next to it, where we had 82% of our field infected. Over 40 minus 30 is 10. And a little bit of quick mental math, 91 minus 82 is going to be 9. And 9 divided by 10, look at me go, is 0.9. My 4th grade teacher would be so proud of me. Now, what do they want us to do right here? Compute the average rates of infection, on that interval here. And what's going on right there, if we cared about units, that's the percent infected per day. So on that 10-day interval here, from 30 days to 40 days, we averaged another 0.9% of our field infected each day. The second one they wanted us to do, and we'll go faster through this now, was after that, from 40 to 50. So let's see what that one looks like. F of 50 is going to come now from this column here. That's going to be a 96 minus F of 40, this one here again, which was 91, all over 50 minus 40. Okay, that's going to give us a 5 over 10, and that is going to be 0.5% infected per day. And the table, if we take a look and go back and let me erase some of the junk that I had here, kind of bears that idea out here, guys. From 30 to 40, okay, we were measuring, let's see, a growth from here to here, and we can see, okay, that's our growth rate. But then from 40 to 50, it looks like that one levels out a little bit. So it makes sense to me that that second answer is less than the first answer, okay? And that kind of makes sense. You're going to lose steam as you approach 100% infection. And the last one here is on the whole interval now, from 30 to 50. So let's see what that one looks like. F of 50 is going to be 96. F of 30 was going to be 82, all over a 50 minus 30. Okay, that's going to get us what, guys? A 14 over 20, and that's going to end up being, let's see, 14 times 5 is 70. So that's going to be 0.7% infected per day. And what we're saying there now, guys, is that this slope right here from the first point to the third is kind of in between the other two. It's not as steep as the first one we measured, but it's steeper than the second one we measured, and so your average is kind of in the middle. That'll make some sense. And the last question here, I think we can do this just on the graph. Draw the tangent line at t equals 40 and estimate its slope. So t equals 40 is this one point right here, and let's remember, everybody, our definition of a tangent line is a line defined by one point on a curve, that's our point of tangency, having the same slope as the curve itself at that point. So if I just had to eyeball it and guess, I would say that my tangent line here for part D looks something like that. Now, how am I going to figure out its actual slope right there? Now, this is an estimate, and every one of us is probably going to do this differently. But if we're trying to come up with the slope of a tangent line, we need to come up with a few key points right here. So this point of tangency, we know had an x value of 40, and I'm going to go to the table right here and say, okay, 91 then was my y value at that particular value of time. And then from there, you guys, after that, boy, it's kind of a crapshoot here. I can't really use the table anymore because that one blue point of tangency was the only one that was actually on the red curve. And there's no guarantee I drew this right, but I'm going to just eyeball and say, okay, that point right there looks roughly clean. That one would have a t-value of 20 and an infection percentage of about 80. So let me slide everything up here just a bit, guys. I think I can do this. All right. Oh, not that. Okay, whoop, whoop, whoop. There we go. All right, so let's go ahead for D here, and we're going to try to approximate the slope of our tangent. But again, it's an approximation, so we're just using the slope formula we've always used with these 2 points here, and that would be 91 minus 80, change in y, over 40 minus 20. And that's going to get us, let's see, a 9 over 20. You could leave your answer like that, but if you wanted that as a decimal, that would be 0.45, roughly then, for the slope of the tangent. And it's just a question of whether you'd prefer your slope as a fraction or as a decimal. Usually we say fractions are a little bit more useful, but I kind of wanted to compare that to some of the answers I had here where a decimal might help. But at this level, guys, both of those answers are going to be just fine. Okay, so that's a wrap on 2.1, number 27.